All right, today we're going to talk about the 12 basic functions. All right, there are 12 basic functions, meaning the ones that we are mostly going to be dealing with. You need to be able to visualize what these functions look like in equation form and in graphical form. And you need to understand their basic properties. We're going to be dealing with all of these functions throughout the year, so learn them all. Okay, these basic functions are called parent functions. They used to be called mother functions, but you can imagine how many kids got in trouble for going home and saying, we learned about mother functions today. So they've changed it now to parent function, although I think mother function is funner because you feel like you're being naughty. Anyway, these are the parent functions of the 12 basic functions. And the reason they call them parent functions is when you take their parent functions and you apply transformations to them, it moves the parent function on a coordinate plane, or it stretches it, shrinks it, so on and so forth. So your transformation reminders, okay, if you take a function and on the inside you're subtracting or adding something from x, it's opposite when it's with your crazy x. Remember, anything inside parentheses with your crazy x is opposite of what it looks like. So this looks like you'd be going left, but it actually moves it right. This would indicate you go right, but it actually moves it left. If you add or subtract a number on the outside of the function, in other words, you add something to the entire function, not just to x, adding moves it up and subtracting moves it down. All right, so the first function we're going to talk about is the identity function, okay? That is f of x equals x. We're used to writing it as y equals mx plus b. Those are all the lines. Those are equations, standard equation for all linear equations. The mother function of all of these is just y equals x, which would mean your slope is 1 and your y-intercept is 0. So it starts at 0, goes up 1, right 1. Okay, that line is the mother function of all lines. You can have other lines. They can move down. They can change their slope. They can move up and over, they could go this way, they could turn around and go negative, but they all come from that mother right there, okay? The next function is the squaring function. So now we're going from a first degree equation to a second degree equation. You know second degree parabolas, the general equation is y equals ax squared plus bx plus c. The mother of all of these guys is just y equals 1x squared plus 0x plus 0, which in other words is just y equals x squared. Okay? This is the mother of all parabolas that look like this. Changing the value of a, b, and c moves this parabola. You can shift this. You can make it wider. You can make it thinner. You can move it up. You can move it down. You can move it over, left, right. Okay? You can move these, but they all come from that mother right there. Okay, the cubing function, now we're going to a third degree equation. General form would be ax cubed plus bx squared plus cx plus d. Okay, that'd be the general form of a cubic, but mother is just y equals 1x cubed plus 0x squared plus 0x plus 0. That's where they get just the y equals x cubed. This is the mother of all of these guys. And cubics look like these s functions, okay? So they kind of make that s-looking shape, that snaky-looking thing, okay? Again, when you change the values of a, b, c, and d, you can make this thing go really wide, you can make it go really thin, you could move it over, you could move it left, you could move it down, you can move it up, okay? You can stretch it out and make it almost straight, you can really widen it out. Okay, but they all come from that mother right there. All right, the reciprocal function. This is when you have 1 over x. In other words, you have x's in the denominator. Okay, and when you put x in the denominator, you usually end up with these boomerang-looking things. And depending on whether it's positive or negative, they'll boomerang either in 1 and 3 or in 2 and 4. They could boomerang this way also. Okay, but generally speaking, when you have x in the denominator, you should expect these boomerang looking things. Alright, don't know why that one's there. The square root property or the square root function, I mean, that's when you have an x underneath a radical. Alright, and when you do this, you get this halfway looking parabola. Now you know when we take a square root, really, if you got the whole picture, because when you square root, it's plus or minus. And if I do the minus part, this is just the positive part. If I graph the negative part, the negative square root of x, it would be this here, okay? But when we just graph the positive side, you only get this top half. So you get half of a parabola going sideways when you have a square root function. Alright, when we have the E number, the number E is an irrational number, kind of like pi. It's 2.7 something, 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 something. And it shows up in a variety of applications. The symbols E and pi were both brought into popular use by the great Swiss mathematician Euler. Okay, that's why they named it E. E was named after Euler. Anyway, this function looks kind of like a log or growth function. It's e to the x. Okay, it goes like this, and it takes off and keeps heading on up. Okay, the natural logarithmic function, that's your ln of x. Okay, this function increases very slowly, so it starts it doesn't go very fast, but eventually it's just going to keep going up and up and up. Okay, this is interesting. If the x-axis and y-axis were both scaled with unit lengths of 1 inch, you would have to travel more than 2.5 miles along the curve just to get a foot above the x-axis. That's kind of crazy. So you can see how slow that increases. Okay, your sine function looks like a wave, and you can tell if it's sine or not. I mean, unless they do transformations. If you just have a regular sine function, sine functions that haven't been transformed will always pass through the origin, and they oscillate between +1 and -1. So it comes up and then goes back down, and it just keeps doing this forever and ever and ever. Your cosine function looks just like the sine function, except for it's been shifted right or left. You'll notice that instead of passing through the origin, at the origin we're up at the amplitude, which is 1. And then it comes down to the 0, and then to amplitude, and then to 0, and then to amplitude. Okay, so sine and cosine look the same, except for sine or one or the other one is shifted over. The absolute value function, that's when you have bars, straight bars. Okay, when you have the absolute value function, you end up with a V-looking graph. Okay, again, we can shift this right, left, up, down, turn it sideways. We can do lots of different things. Okay. But the mother of all these V's come from the absolute value function. The greatest integer function is easy to recognize because it looks like stair steps if you connected them, which you don't do, but that's where it came. They also call this a step function. Its real name is called the greatest integer function, but it's often called a step function because it kind of looks like you're walking upstairs. Okay? And we have the logistic function. The logistic function always makes this S shape through two horizontal asymptotes, one of them being at 0 and the other one being at this constant, whatever that constant value happens to be, depending on how this is shifted. And then the curve will go asymptotic to the asymptotes and turn somewhere in the middle. Alright, so now that you know your 13 functions, it says match the function with the graph. Well, I know it's a V shape, so I know it's absolute value. And I also know it's absolute value because all of my choices have absolute value in it. Mother would be right here. So what they did is they went 1, 2, 3, 4, 5 units to the right, which means that in my bars with X, to go right, I have to do it with X in the bars, and to go right, I would actually have to subtract 5. Okay, so that would be my solution, which is this one. This one would be 5 units over this way. This would be 5 units to the right, but it would also be 1 unit up. So this one would look like that. This one wouldn't move right or left, it would just move down 5. This one is the one that moved to the right. Okay? So you try this one, hit pause, come back when you're ready. And hopefully you got this one. Okay, I see it's a parabola, so I'm looking at mother function being y equals x squared. Well, first of all, they've turned it upside down, which means they've made it negative. Okay, the next thing I notice is that they've moved it 1, 2, 3, 4, 5, 6 units to the right. That means the negative's outside, the square's outside, but to go right or left, you have to do it inside the parentheses with x. And to go right 6 would mean that I subtract. And there would be my function. Okay, you try this one, hit pause, come back when you're ready. And hopefully you got 2. Alright, the reason I know that it's sine and not cosine is because if I move this back down and put it back down here, it would do this, which means it passes through the origin, so I know it's not cosine. Okay, and then this would be mother sine, and it looks like all they did was move it up 4. So if it was right or left, then I would do sine of x plus or minus 4. This would be moving it left. If you want to move it up, you don't put it in parentheses with the x, you put it on the outside. This would move it up, whereas inside parentheses would move it left. So there's my equation. This one would move it down 4. Alright, so we've been talking about recognizing these graphs. And they want you to briefly describe the graph of the 12 functions. What I would do is do the equation and then sketch a picture of what it looks like. Alright, so next part of your homework is they're going to ask you to, pick out certain ones of these functions based on characteristics. So like for this one, and this, they're just listing all of the 12 basic functions, okay? They want me to figure out the 3 functions that are even. If a function is even, the y-axis has to split it in half, and this half has to look like the other half, which it doesn't. If this was even, it would look like that. Okay, so no. Here, the y-axis splits it in half. This side, if I flipped it over, would be this side, so that's even. This one, again, if I flipped this over, I would get this side, so that's an even function. This is not, because if I flipped this side over, it would be that. This isn't, because if I flip that over, it would be there. This is, because if I flip that over, it would be here. The y-axis splits it in half, so that's even. None of the, well, there's all 3 of them, so there's only 3, and you can tell the rest. This is not even. This is not even. This is not even. It would have to do this. And the sine function isn't even either, because if I flip this over, it would actually look like this, not the blue. So that one's, sine is not even. This one's not even. And this one's not even. Okay, so those are the 3 that are even. Alright, they want you to find the one function that's decreasing from 0 to infinity. So hit pause, come back when you're ready. And hopefully you got 1 over x. Decreasing from 0 to infinity means starting at 0. So I'm just looking at this half of the graph. They want to know if it's decreasing. No, this is going up. This is going up. This is going up and down. This is going up. This is coming down. So there it is. I can check the rest of them, but this side's going up. This side's going up. This side's going up. This side's going up. This side's going up and down. This side is going up. And this side is leveling out. This one's going asymptotic or horizontal. So the only one that is decreasing, in other words heading down from 0 to infinity, is the 1 over x function. Okay, this one they want you to find the 2 functions with infinitely many zeros. Hit pause, come back when you're ready. And hopefully you got sine and cosine. Infinitely many zeros means x-intercepts. This has 1 0. This has 1 0. This has 1, 2, 3, 4, and this will keep going back because it just keeps oscillating. So there's 1. That has 1 0. That has no zeros. That has 1 0. That has 1 0. That has 1 0. That has a couple. This has infinite too because this just keeps waving, and every time it crosses the x-axis you get another 0. This has 1 0. This has no zeros. So those are the two that have infinitely many zeros. Alright. We can talk about the symmetry. Alright, x-axis symmetry, even or odd. Alright, so we are at homework, which means we are done. So happy homeworking, and I will see you next time.